Welcome to this next Reigate College Physics YouTube video. This particular little video is about how to explain how a simple electric motor works. So this particular video supports part of your learning for TRA 8. So TRA lesson 8, and at the end of that lesson you have a question. It says explain as clearly as you can using the appropriate A2 level physics terms what happens when the current is turned on. Add lines, arrows and or labels to the diagram to help you. Okay, so where shall we start? The best place to start here is by labelling the diagram as much as you can. A well-labelled diagram helps you to describe what is going on really quite easily. So what we're going to do first of all is to mark on the magnetic field lines. Magnetic field lines, as you will remember, go from north to south, and you've got a nice uniform field passing from the north pole of the magnet to the south pole of the magnet there, and we'll add our arrows like that. Okay, so there are magnetic field lines. Now what I'm going to do is I'm going to label the motor coil itself, and I'm going to label the corners of it, A, B, C and D. And this is so that we can talk about what is going to happen with this motor. So the first thing that you can say in answering this question is what is happening to the field lines. They are going from north to south. The field is fairly uniform between the poles of this magnet. So that can be our first point. So we have a uniform field, and that goes from north to south. You'll also notice that in black around here we have the motor coil there, A, B, C and D, and the current is flowing in a clockwise direction, so that's point number 2. So we have a clockwise direction for our current. So it would be a good idea to mark on the diagram the current directions. And there they are. Okay. Now you know that a motor is going to turn. If a coil is in a magnetic field, the current carrying wire will experience a force if it is at right angles to that magnetic field or is at some angle that is not parallel to the magnetic field. So the first idea that you're going to use with this one is to say you're going to apply Fleming's left hand rule. Okay, so in order to help you, you would then take your hand. Remember, you need to have your thumb, first finger and second finger, all at right angles to one another. And what you're going to do, if you remember, your thumb is for force, your first finger is for the field, and your second finger is for current. So it goes in the order of FBI, not CIA, the FBI, all right? So we know that B goes from north to south. We also know that the current on side AB is going that way into the page, in which case we're going to have a force which goes up the page. So what we would do is I would label side AB as force AB. You would then apply Fleming's left-hand rule to side CD. So this time our field is going from north to south, but this time our current is now going back down the page, which means my thumb is now pointing into the whiteboard. So my force for side CD then goes down the page. So what you can do now, point number 4, is that side AB experiences an upwards force, and that's due to Fleming's left-hand rule and the fact, so this is because I and B are perpendicular. So there's my shorthand for perpendicular, so right angle with a apostrophe, then an R. You can also, for another really good point, say that side CD experiences a downwards force. So point 5 is side CD experiences a downwards force. Can you see how much easier it is once you've actually labelled these different parts of the diagram to now be able to talk about them? But you're saying, well, what about the other sides of the motor core, side BC and side AD? Well, let's rub out those first few points just to give us a little bit of room. Side BC, you'll notice, is parallel to the magnetic field. And if it's parallel to the magnetic field, then Fleming's left-hand rule doesn't really work. Remember, F equals VIL sine theta, and theta is the angle between B and I. If the angle between B and I is 0 or 180 degrees, which it is here, so you've got basically inside BC, your current and your magnetic field line are anti-parallel. So you've got current going around that way, B field going the opposite direction. Sine theta becomes 180. Our force is 0. So inside BC, force is 0. That's going to be the same for side AD. So side AD is also force is 0 because B and I are parallel to one another. And so you've already been able to say at least 6 different points on how the simple electric motor works. We can certainly add to that if we want to. So what we can talk about also is the moving brush contacts or the split ring commutator. So let's expand on that just a little bit now so that you can see what happens with a split ring commutator. In order for the motor to turn in a consistent direction, you must always have the wire that is adjacent to the South Pole with the current going in an anti-clockwise direction. Now, imagine what would happen if side AB flips up and over so that it's now adjacent to the North Pole. If it connected directly to a negative current, then what would happen is there would then be an upwards force, and it's all going to get very, very messy. It's not going to work at all as a motor. So what needs to happen is you need to have these two little wires here that are consistently a positive on the left side and a negative on the right side. So let's imagine that you have a battery pack over here, okay, connected to some wires. Now, what in reality you're going to have to do is have these as very slightly separate contacts. So you're going to have some kind of brush that kind of just touches the outside of those wires. So we have a brush contact. Although that's not very well drawn, what's going to happen is side AB is going to go up and over to side CD, so that then when it's on that side, it then connects to the negative side of the battery. and then when side DC flips underneath and goes to side AB, then that's going to connect to the positive side of the battery. So it's always feeling an upwards force adjacent to the South Pole and always a downwards force adjacent to the North Pole. So this is called a split ring commutator. I am sure your teacher will show you a proper engineering diagram of what that really looks like. But it allows the motor to turn in a consistent direction. You don't get your wires all muddled up, and it allows for smooth, effective running of that motor. So I'm hoping that gives you some pointers then for how a simple motor works. You could have written either 8 or 9 different points there. So to summarize, current will flow in a clockwise loop from plus to minus. You've got a uniform B field from north to south pole. There's no magnetic force where the current is parallel or anti-parallel to B, so that side BC and AD have no force along it. But sides AB and CD do, because current and magnetic field are at 90 degrees to each other, so there is a force. The size of that force is given by Fleming's left-hand rule, F equals BIL. The two sides, AB and CD, because the current is going in opposite directions, you have opposite forces. So the left side is going up and the right side is going down. So you've got a clockwise spin of that particular coil. So you can draw an arrow perhaps to indicate the idea that you have a clockwise spin of the coil. If you have a DC power source, then you must have these brush contacts, and the contacts are going to swap every half turn with the brushes so that you get this consistent turning direction. So I'm hoping that helps you a little bit on understanding how a motor works and hopefully understanding how to put things in a nice logical order. Okay, thank you and see you in the next video.